Hello, I'm Xavier Manzano. I'm going to do a presentation on experiment 3, which is finding the drag and lift for a Clark Y13 airfoil with a leading edge slat and a split flap. For this presentation, I'll be showing you what our experiment objectives were and what we had to find. Give you some background that we were given for this specific experiment. Talk about what steps were taken during this experiment to execute it. Explain some of our results that we were able to find, and then give you some final conclusions that we were able to get from the experiment. So first off, our objectives. What we wanted to find was the lift and drag coefficients of the wing at with four specific adjustments. First, actually would be like our control, and it would be a clean wing with no adjustments, no flap or no slat. Then we want to test with a leading edge slat, and then we want to use the wing with only the flap deployed at a 45 and 30 degree angle, and then we want to find both with a slat attached and the flap deployed. So all of these will also be tested at various angles of attacks. I think that's very important to consider because we want to find out when stall would occur with these lift devices. And the stall can be observed when actually performing the experiment because of the tufts that are on the wing itself. You can kind of see on figure 1, there are pieces of thread, and if they're not flowing along the camber of the airfoil, the wing, then you could obviously see there's some stall occurring. Also, we want to find the pitching moment based on the aerodynamic center of the wing, and we get that based off of the pitch moment center of the balance. So when it comes to this experiment, the major thing to consider is to account for the wind tunnel. So when the wind tunnel does not give us real results based on how wings will behave in the outside world. In the outside world, wings of an airplane are an open space with infinite amount of space and no enclosure. And the enclosure from the wind tunnel gives the streamlines a straighter streamline, whereas in real life these streamlines can be more curved. And so to adjust for that, you would need to know the wingspan of the wing you're dealing with, the dimensions of your enclosure or your testing area, and then also you also need to know your chord length, and that was already done for us, and in our lab manual was given by those two equations right there, so we could find the actual adjusted angle of attack by using 1.7 times our observed lift coefficient. And then also we want to correct our drag coefficient, so we would also multiply that by the square of the lift coefficient by 0.03, and that will give us the actual data of a real life application. And the sting balance gives us reading normal to the wing and the axial force that is applied kind of along the chord of the airfoil. And to find the lift and the drag, you need to use the angle of attack and manipulate it in the same way that you can see here, so that you could find the actual lift and drag based off the readings you get from the sting balance. So for the actual experiment, first we needed to calibrate our sting balance and find the pitching moment center of the balance. So as shown right here on the figure 2, to find that pitching moment, we want to place weights on the set screw, which is where you would mount your wing, and then find when the reading reads 0, and that would be your moment, and that would be your your moment center. And then to calibrate the forces in each direction, X, Y, and Z, you would need to use weights as well until you get a 0 reading for each of the forces. And then all you need to do is use the wing, set up the wing in a way that you want to run. So first you want to place the clean wing with no adjustments. Record your data, then remove the wing, because you shouldn't actually manipulate the wing inside the testing section. So you want to remove the wing, do any adjustments, and then put it back in. And then collect your data, and then either change the angle of attack from the sting balance, or you need to adjust your flaps. And you keep repeating collecting data from the sting balance. So some of our results came in that the moment center was found at 58.64 millimeters about from the end of the set screw, which is about from right here. We want to find the moment center, so about 68 millimeters to the left. Also, okay, so that's what it's given for that. And then for lift, we found that when you add a flap, which is the gray and yellow data points on the graphs to your right, you'd see that you get increased lift when you have a flap included. However, when the slat is included, you get the same amount of lift. However, you're able to maintain that lift at larger angles of attack. So you can see here that the gray dots, that's with both a flap and a slat. So the slat is able to maintain this lift coefficient of about 1.5 into steeper and steeper angles of attack. And you can see here when it's just the slat alone, it's slightly less lift. However, we reached the same amount of lift as a clean without any adjustments, but we're able to maintain it for about more steeper angles of attack. And then when it comes to drag, however, the trade-off with flaps is that you get increased drag. So you can see that the yellow and the grays are way steeper and reach higher points than than just with the slat or with the clean. So this shows us that there's a trade-off when it comes to deploying flaps and such. And then when we notice, we also tested the different angles that the flaps are deployed. So when you have a steeper flap, such as the blue points, when your flap is at a steeper deployment, your lift is significantly increased because you're changing the camber of the wing. So you're allowing you're changing the pressure and thus creating more lift. However, that, as seen before, comes at a trade-off where drag is also increased. Not as much, not as dramatic. However, it is increased. And your lift to drag ratio doesn't change much with the different flap angles, but this is one main takeaway when trying to design a wing, that your flaps will increase your lift, but there's also a consequence of more drag. And so, as explained before, lift flaps really help with lift. That's why the wings have them. When you want to take off, you need to increase your lift so that you can actually take off, and then so that given your speed, you can actually pitch up and lift off from the ground. But for slats, you don't really get much more lift, but you can sustain the same amount of lift throughout higher angles of attack. And slats decrease with drag. Slats decrease in drag. Yeah, slats decrease drag slightly, but flaps will increase it. So that's basically it. Here are some of my references. This is the lab manual, our our actual lab report, and then also just wanted to give credit for some of these pictures I was able to use from the lab videos. I want to thank you, Professor Coster, and to the TAs for helping us get the best experience as we can given the circumstances. I was really looking forward for this lab. I would have loved to do it hands-on. I really love airfoils and such, but thank you very much for all your effort. We really appreciate it.